It is my pleasure to introduce Jan. We met in real life just last week ago, and he's fantastic and doing brilliant research. So I am so excited to be able to introduce him. He is a PhD student at the University Medical Center of Utrecht. His research focuses on designing circular medical devices for dialysis and eye surgery. He holds a master's degree in Biomedical Engineering from Delft University of Technology and a bachelor's in Mechanical Engineering from National Taiwan University. He has worked for several years in medical device industry as a mechanical engineer in both manufacturing and R&D. Born in the Philippines, Jan is interested in how state-of-the-art technologies can shape the next generation of medical devices to improve accessibility in low and middle-income countries while promoting sustainability in more developed healthcare systems. So, Jan, it's my pleasure to hand over to you if you'd like to share your presentation and go ahead.
Okay, yeah, thanks. I'll share my presentation just now. Yeah, can everyone see my screen?
Yep.
Yes.
Okay, yeah, thanks Furat for the introduction. I think he already introduced me well enough, but today I'm going to be talking about my research and giving you a short overview of what we're doing here in UMC Utrecht. It would be about reducing energy and consumable use, particularly in the production of dialysate. And this is an overview of the project I'm doing. So I think probably all of you know that dialysate comes from mixing pure water and concentrates. So I think for an average dialysis session consumes 180 liters of dialysate, and a lot of it is from pure water, and it's mixed with 4 liters of acid solution and 530 grams of bicarbonate powder. And here in the right, you see the whole process. So it comes from water supply and raw materials. And we have water purification, which produces the pure water, and the disposables, the concentrates, are bought from manufacturers that supplies them. And pure water and concentrates are mixed with the HD machine, and it's delivered to the patients. Yeah, and what I'm doing here, there are several projects going on. So first one is the RO optimization. So we try to look into the water purification or the system in Utrecht, and we try to make the best use of it. So we try to optimize the settings and see what we can save from not changing our machine. And we also look into the concentrates that are used here in Utrecht. So first there is the acid canisters, and now Utrecht also changed to acid delivery. We just published an LCA study about this last year. So generally, central delivery is more sustainable than using large canisters individually for each. And we also look into the bicarbonate side. So we did a project on redesigning the bicart to make it more sustainable. So I'll talk about that later. And then we also have another project about forward osmosis. So instead of mixing pure water and concentrates, which is quite energy intensive to make this pure water, we have an alternative process called forward osmosis that can also produce the dialysate, which we need. And it's much more energy saving, and also very saves a lot of water. Yeah, so this is the paper we just published last year about central acid delivery, and it's LCA about how much more sustainable and even accessible in other countries for central acid delivery. And so the first project I'm going to talk about is about RO optimization. And just a quick overview of what the RO is about. So it's large volumes of water is used in HD, and it also consumes a lot of energy and raw water because it needs a lot of high pressure to push the water through the membranes, generate that the pure enough water that can be used in dialysis. And therefore, we are investigating and trying to optimize the efficiency of this system and to reduce water and energy consumption. This is the system, a simplified schematic of what our system does. So it goes through pre-treatment and the purification stage where the RO unit is working. And there's also a disinfection unit, which disinfects the lines every regularly, sometimes several days a week, sometimes every day. In our case, in UMC, we disinfect them every day. And it distributes the water throughout the distributing line to each patient connected to these lines. So the job of this RO unit is to, of course, generate the purified water, but also to maintain a sufficient permeate volume and low conductivity and low germ count throughout the time the treatment is needed. So what we did is we tried to measure what we are using in UMC Utrecht. We installed electronic flow meters, ultrasonic flow meters in the RO unit, and we did measurement, and we got graphs like these. So we tried to map them to our treatment schedule and see whether how much we consume during those treatment, and we try to calculate them. So bless you. So on the left you see the consumed water we measured in the distribution lines, and on the right we see the discharge water, which is the reject water from the system. So this is a example on measurement on Sunday. So as you can see, there's the disinfection, which some water is used for cleaning the lines, and then in the morning there's no patients, so there's no consumption in the lines. And so the water is still produced, but it's recirculated, so there's no consumption. And then after around 1 o'clock, the treatment starts, and then there's consumption. And after around 8 or 9, the treatment are done, and then the ward is closed. And you see in the discharge water, you see how it operates, the behavior of the system. So it flushes water regularly, so reject water, but throughout the whole day, it actually rejects, because it also needs to maintain the flow. So although there's no consumption, but there's still constant reject water, just to maintain enough water, just to be sure that there will be water if anytime the water is needed from the machine. And we also installed energy meters on the energy. So we measured the power needed. So this is for the left, you see the RO unit, and the right, you see the disinfection unit. And the same in Saturday, and it's also a half-day session. In the morning, there's more power used, but in the afternoon, there's no treatment, but there is still some power used, a bit lesser. And disinfection, of course, in disinfection, it uses power, but the rest of the time, it's not working. So it's, this is what we see. And what we found through these measurements, so we measured actually a total water use of 46,000 liters throughout the week. And in average, it's around 300 liters per session. And we also found that recovery rate here is 53%. So it's not a high number. I think in the specifications of this machine, we are able to reach 85%. I think we set it into 66% in the settings, but also we need additional water, and there's also some inefficiencies. At the end, we measured 53% of actual that the water actually is used. So it also means that around half of the water is just rejected and not used and dumped into sewage. And total energy use is 360 kilowatt hour for the week. And per session, it equals to 2.4 kilowatts. And yeah. So what we are trying to do, the next step, we'll first, of course, try to increase the conductivity, which directly influences or affects the recovery rate, the efficiency of the machine. So we'll try to increase it from 3 to 5, and hopefully our recovery rate would rise from 66% to 85%. So the maximum the machine allows. Because I think in Netherlands we are able to do this because our water is also relatively clean. So from the reject water, it's what we found in the reject water is also quite clean. So we tend to push the limits a bit more. And we also plan to turn off the machine outside treatment hours, because we found that although there's no and it's not in use, but just putting it, just letting it operate and getting on standby, it still consumes quite a lot of water and energy. So I think by simply turning them off when there is no patients, and would save quite a lot of energy and water. But in alternative, we also need to prepare some backup mobile RO systems, which can be used in case any emergency treatment is needed in the ward. And we can, of course, reduce flow of the machine, but there's a limit because it's already defined in the specs that how much flow the capacity this machine is designed for. And I think another long-term, probably not part of the optimization plan, is I want to just mention that there are always newer machines available in this market, and usually there also are more energy and water saving. For example, this machine I'm showing here is from B. Brown, so we use the B. Brown machine that was installed several years ago, but now they also have demand-driven machines. So meaning that they only produce the water they need of how much water is actually consumed. And they also adjust the motor frequency and lower it a bit if not that much water is used. So it saves much more energy. And yeah, but I know it's not possible, at least in the short term, because investments needs time, but at the meantime, short term, we're trying to optimize what we have already in the ward. Yeah, and next, this is a bicart redesign. So after the RO, explaining about the RO, we also look into the concentrates. So we also look into the bicarbonate concentrates. The bicarbonate powder is also used in dialysate production. So this is you see the picture. This is all bicarbonate powder cartridge used in our ward, and one is used per session. So in UMC Utrecht, we have maybe around 7,000 sessions, and that would equal to 60 tons of this product alone. And we found that there are central delivery systems available in the world for this, but unfortunately, they are not available in Europe. So I think, for example, the acid canisters, we also used to use acid canisters, but we switched to an central delivery system, which saves a lot of waste and also human labor. But for the base part, bicarbonate part, it's not possible, at least here in the Netherlands. But it's actually, we found it's quite common in Japan, China, or Korea. But they also have a different context. They have larger dialysis centers, more population that does dialysis. So the setting could also be a bit different from what we have here in Europe. So what we decided is we try to dig into this product and see what we can do about this product. So first we did a waste audit. So we collected all the bicarbonate cartridge used in a week in our ward here in UMC. So for the whole week, we collected them, we weighed them, and we also recorded the treatment that used this particular cartridge. And at the right, you see the graph we made. So there are 2 hours, 3 hours until 4 hours. So there are different treatment durations. And we also measured how much bicarbonate powder is left inside the bicarbonate. And so what we found is 142 is used per week. So that meant we have 142 patients that week. And what we found is 47% of the powder is left unused. So aside from the plastic itself, actually quite a large amount of powder is still inside the bicarbonate. And that also means that 48 kilos of powder and 12 kilos of plastics ends up in incineration. And if you look at the LCA of this product at the left, 56% comes from the bicarbonate powder. So actually more than half come from the content inside, and 21% comes from the plastics, the manufacturing of the plastic packaging, the PP, and 13% from the end of life, like incineration and transport to that, and 10% comes from transporting the product from the manufacturer. So it's actually a lot of unutilized powder, which also contributes to a lot of carbon emissions. So what we try to do is we try to design a reusable bicarbonate cartridge, and you see in the right figure, so we have the linear system, so which is normally done. So we manufacture a single-use cartridge, it goes to the hospital, used in the patient, and then it's disposed. And because the powder is still inside the cartridge, it can only be disposed in general waste and incinerated at the end, which is also a pity for the plastics, because it's also very good plastics. Even you dispose if you need to dispose the powder, we probably can recycle the plastic still, but because it's made so sturdy and it's very difficult to separate, usually it just ends up in general waste. We try to design something, we try to think, what if we have a circular system on this? So of course it's still manufactured and then goes into the hospital. But first we have to design something that can be separated, so it can be opened. The residue is still dumped in the general waste. The packaging is collected and then cleaned in disinfected, and then filled again with new powder and then sent back to the hospital. So by this way, we try to create a circular system, so not wasting the packaging, but also by refilling only the powder that each hospital needs. So the idea is that each hospital have different requirements for the amount of powder they need, but usually in manufacturing, it's because it's high volume, they can't kind of personalize the amount of powder. But here we also try to give that option to the hospital to just fill the right amount of powder so that there will be less residue. So this is what we designed in Delft with a student. So this is, she called it BiCare. So if we did printed the cartridge, and you see there's a silicone cap attached on top, which can be detached and cleaned easily, and also it's not lost. It holds in place with the container so that it doesn't get lost, which normally does in normal treatments. And it's also a semi-transparent container, which you can see how much powder is still inside. And you can also open it and clean it and then fill it with new powder. So we did analysis on how much impact this product can have. So if we have the bicart, the normal bicart, single use, around 1.6 kilograms of carbon emission. But one single bicare, the reusable one, would be more like 3.4 because it has more materials, it's more complicated, the casing. So it has a bit more carbon emission. But after several uses, like if you use it twice, it's still more. But if you use it 10 times, for example, then it can reduce carbon emission by 33%. And you can use it 50 times, 500 times, and it continues to decrease. But I think the point here is that we think that 10 times probably is already enough to make a big impact on reducing carbon emissions. So we don't need to go after 500 times. 50 times even is already a sweet spot. It already shows that these kind of reusable products don't need to be reused forever, but we just need to reuse them several or good enough times, and then we already can have a very. And I think also one takeaway from our research here is that we also found that we can probably already do some things without this product. Well, we can already optimize the cartridge sizes. We already found that the cartridge we order here in UMCU is too large for most of our treatments. And we can also like order two different sizes. Like for example, 2 and 3 Rs, we use one size, 3 and 4R, we use a different size. And we can also try to recycle the cartridge. So if we simply separate the cartridge, we can also recycle both the bicarbonate and the plastics. And in fact, I think B. Braun is actually already doing that in Germany. So in their clinics, they actually send back all the bicarbonate cartridge, and they separate it in their factory, and then they recycle both the powder and the plastics. But unfortunately, it's not possible to join their program because we're in Netherlands, and it's kind of a bit tricky to transport waste across the border. But if we were able to join this program, I think it would be also a nice initiative to reduce the impact of bicarbonate cartridges. Yes. And the final project I would talk about is the forward osmosis. And so first, I want to explain a bit about how normally dialysate is produced with RO. So we need a fairly high pressure, 15 bar, and tap water is pushed through a filter, a membrane, semi-permeable membrane, and then there is discharge water and then pure water. So in UMC Utrecht, from what we measured in the RO optimization, we already know around half of it is discharge and half of it results in pure water. And this pure water is mixed to bicarbonate and the acid concentrate. And then it becomes the dialysate, which is then used in the patient. So we are now investigating in an alternative to RO-based production of dialysate. So there is another kind of membrane that uses FO, forward osmosis, And compared to the high pressure that is needed in RO, only it uses very low pressure, so only 0.5 bar is needed. So it's very energy saving because you no longer need to push the water through the membrane. And instead, it uses the osmotic pressure difference between tap water and concentrate to pull the water from the tap water and still have pure water. And it's mixed gradually with the acid. So it's a natural process which uses lesser pressure. So you see in this graph, tap water is passed through one side of the module, and then as the acid concentrate is in the other side. So the osmotic pressure difference water, and then it dilutes this acid concentrate. And then after the module, it becomes diluted to what we need. And then we add bicarbonate inside and becomes the dialysate, which can be used with the patient. So this process is called forward osmosis, and it's actually quite widely used in, for example, desalination and also food industry. But now we're also trying to investigate whether it's possible to use the same technology in a medical field. So first, we try to characterize the membrane, so to understand the performance of the membrane. So this is the setup we have in our lab. So we have some scales to measure the weight, the volume, the flow of the dialysate, the concentrates. We have our membrane in the middle, and we also have pH meters, conductivity meters, and flow pumps. We did so different dilutions of concentrate and also different flow speeds, just to see how it performs. So, and then we try to model what we characterize. So from the experiments we got some parameters of the membrane, and we modeled it within this equation computationally, and we got this graph from the left. So in this graph, basically it tells us how the process goes within the module. So as you see, the blue line, it's the water flux. So how much transferring from one side of the module to the other side of the module. So initially, when there is still very concentrated acid, the water flux is quite high, and then it drops very fast at first, and then kind of steadily drops until the concentrates are diluted. And the orange line, you see the dilution factor, so how much concentration the concentration is. So we start at 1, and then it increases until 45, which is the target we want for dialysate fluid. So here in our setup, we place 2 modules in series. So it first goes into one module, and then it rises to around 30 diluted 30 times, and then the second module where it continues to dilute the concentrate until 45 times. So we were able to model the dynamics of the dilution process, and that's what I said. The water flux drops, but the dilution continues and rises. Yes, so it reaches 45 after we use 2 modules and connected in series, and the draw flow initially, the flow of the concentrates is 0.9, but hence yes. So we calculated how much the water efficiency. So we expect 90% efficiency. So it also isn't 100% because it needs the pressure gradient, so it needs osmotic pressure difference to operate. So if one side the concentrate, the water gets too concentrated or too dirty, then it also loses the osmotic pressure difference. But compared to what we have now with the RO, it's still quite high. And especially we save a lot in the energy use. And that's mainly because there's the large difference of the system. So in our setup, we only use 0.3 watts per hour per liter of water added to the dialysate. So this is only 4% if we compare it to RO. And it's still a work in progress. So we are still experimenting on this membrane. We're still trying to improve our model and measure the solute loss. So I think that's one concern, that the membrane is not perfect. Some solute might move from one side, the concentrate side, to the tap water side. So there might be some solute loss, but we have to measure that. And if we include that in the modeling, we can also adjust for that solute loss and still have the same concentrate of what we have targeted. And then the next step would, of course, make a proof of concept of the dialysate production. So we'll build a setup that makes exactly the dialysate production we need in the ward. And I think that's it. So thank you for listening. And if you have any questions, yeah, please. Yes.
That's superb. Thank you so much for that presentation, Jan. Just yeah, it's amazing to see the amount of work that is coming out of UMC, and so it's a real privilege to be able to have you present 3 sort of distinct projects that all contribute to more sustainable kidney care. If people would like to turn on their cameras, if they are comfortable to do so, and Jan, if you'd like to finish sharing, then we can move to discussion, and I open up to the floor if anybody has any questions.
No, thank you, Ian. My name is Susana Carvajal Arjona. I represent Federation of Patients with Renal Kidney Diseases, Rare and Genetics, different patient organizations across Europe. So for us, it's really inspiring to see you how the science are doing for improve dialysis patients' life, quality of life, because this is important, but always protecting the world. So thank you very much for your contribution and your work.
Thank you.
Gareth, go ahead.
Hi, Jan. Yeah, really interesting talk. Lots of really good ideas there. A couple of bits from my long experience in this. We've had heat ROs for 20 odd years now at the Royal Free. We used to do a loop disinfection every night. Over the past 10 years or so, we've cut that back to once a week. Achieving an AO of 16,000 on the loop, and we do once a week on the ROs themselves. We've seen no deterioration in results. So I know lots of manufacturers say, oh, you do it every night. I don't think that's entirely necessary if you've got, you know, a reasonable standard of loop. And the other thing I was going to say was, we've measured the total water incoming into our RO system, right into the pre-treatment tank, and then we calculated how much we used in every single treatment, and we got about 52%, and we're using, it's a CWP 800, so it is one of the demand things, but so we're losing 50% of the water, but that includes the RO clean, the machine disinfections, and, you know, everything else that needs to be done. So overall we're getting just over 50% of that I just thought I'd make those points. So.
Thanks for your comment. I think we also Hus is also in the webinar. Hus is also Utrecht, so we totally know what he totally knows what we're doing. We also have discussed about reducing our disinfection frequency. We do it currently every day, but we don't know why we do it every day. Actually, we asked B. Brown. B. Brown was also involved in the discussion, but he also doesn't know why. Probably just history. But actually, B. Brown 3 days a week, which is lesser than what we do now. But still, there's some resistance in the ward, and I think that's also because we have some reports that shows contamination on the water, but it's not really about. Sometimes it's very hard to know where that contamination come from, or probably it's just from the assay or from the sample, but that also makes the ward or the clinic more hesitant to reduce our disinfection cycles. But I think what we will do is we'll try to do it step by step. So we already have a lot to do. First, of course, we just recently turned off the off treatment hours, the RO and off treatment hours. So that already saves quite a lot. We're also adjusting the efficiency. So the increase. I don't know why it's still. I think you have a fairly new machine, and it's 50%. We also measure this similar, and we hope we can. I think B. Brown is also a lot involved in this project, so they're going to help us with it. I think for now we adjusted the conduct fee, but from the results we can't see a lot of change, and I think it has to do with also the periodic flushing of the membrane, which limits the efficiency. So because of the safety precaution, they still flush it, and it's very regularly. So yeah, but we'll see. Hopefully we can increase our efficiency even more. Yes, but thank you, Gareth. Thanks for also sharing your experience. Yep.
Before I go to you, Keith, Hus, did you want to come in on that point? I saw you unmuted.
Yeah, I'm muted because there might be a question from Jan, but there wasn't. He was able to answer the question of Gareth definitely, so it's not a problem. I can share something else. Jan was talking about reuse by redesigning the cartridge itself, and I can add to that we are looking into reuse of the current cartridges as well, by using them twice, like once in the first shift and use the residue for the second shift. And we were able to do that by switching our HD machine off after priming, so that we can calculate the amount of bicart used per machine hour, and by doing so we were able to do 3 hour shifts with a bicart cartridge of 720 grams, which is quite less than the 530 grams Jan mentioned in his presentation. So, and it would really reduce the carbon footprint, of course, because we can use the bicart twice. So this is an ongoing project for work package 3 in kidney care at the moment.
That's great to hear. Yeah, that figure of, I think it was 47% of the powder remains unused stuck out to me as well. So yeah, when results are in for that part and you want to present, just let me know, because it would be great to hear more about that. Keith, go ahead.
Yeah, thank you. Great presentation, Jan, and some really good innovative work that you're doing there. And I've really put my hand up to make an offer. The Sustainable Healthcare Coalition is hosting a circularity forum for industry and health system to come together and discuss common issues. It's not specifically related to kidney care, but would love to see you bring a discussion of these bicarb cartridges to that circularity forum. The next meeting is tomorrow, and I can't believe that you're going to be available at the drop of a hat. But if you could allow me to use your email addresses, Jan and Goose, I'll make that introduction to see if we can get that story come along to our circularity forum. And one of the members of the forum is B. Braun, so you can poke them and ask them why they're not doing a better job for you.
No, but B. Brown is also one of our partners, so we have a lot of conversations, so they totally know what we're trying to do, and I think they're very supportive. Yeah, but they also have their own perspective, and they also have their own business. So yeah, but
this issue of being able to move things across national borders to make that circularity loop really work is a common problem.
Perhaps good to add, we are exploring it together with B. Brown, whether we can transport the bicarbonate waste across the border to if you market as reuse, because actually the plastic is being recycled and also the bicarbonate is being reused for other purposes, non-medical purposes. If you can market as reuse, it may be allowed. So the legal persons here and from B. Brown are together exploring whether we can join their pilot in Germany. And we have a lot of hospitals here that would like to join this pilot. So Amsterdam, Leiden, Nijmegen. So yeah, it's still ongoing, but yeah, perhaps good to add.
The more people discuss these issues and say that they've got an interest in it, of course, the more the drive is to actually find solutions to this that work for everyone. So it's important to share the message. Thank you.
And speaking of sharing that message, the conference that you have tomorrow, if that's open, and feel free to put a link in the chat so that draw people's attention to the work you guys are doing. Marta.
Hello, Mark. I think you're muted.
It doesn't say you're muted, but we can't hear you. Alternatively, if it's a quick question, do feel free to type it in. Gareth, in the meantime.
While we're waiting for Marta to sort out her IT issues, I've said this before in these meetings, and I'll say it again, whether it's dialysers, acid concentrate, bicarbonate, my view is that the era of the single-use medical device has served its purpose, and we need to look at the way CE marks work and the way that it's implemented, because this is blocking so many things that we know happen all over the world. You know, we had the talk with dialyzer reuse and all the rest a few months ago, and again they do it in America. It's absolutely standard. So I just think as a general thing we need to really look at that in a hard way if we're going to make really significant gains, because I think it's really holding us back.
We totally agree. We also have a project on dialyzer reprocessing, reuse. We're also looking into that. It used to be standard in quite a long time ago, 20 years, but it moved to single use. But we also understand the reasons why it's become single use, of course, convenience and that. So we also will look more into that and probably have a better solution, not only going back to what we did before, but also think of something better. Yeah, but I think that's a very nice point.
Yeah, and Jan, I think you can also add about the regularity. regularity issues, because MDR actually allows it. Yeah, you know better, but you can perhaps comment on that.
Yeah, so I think there's a lot of new progress on regulations. So it wasn't clear where the responsibility was before, but I think recently they passed reprocessing, defined it quite clearly, and also in Netherlands at least, and I think also some other countries in Europe, they also defined whether it's allowed to reprocess devices. So not everything we need to rely on the manufacturer alone, but some, like for instance, the dialyzer, it's also allowed that the hospital reprocess it and takes responsibility. And it even allows a third party to reprocess it for the hospital, and in the condition that it's returned back to the hospital. So in that case, we don't really need a new CE mark. Of course, the quality rules still apply, but I think that the regulations made it quite clear and also shows a quite clear path on how people can move on. And I hope that it was only passed last year in Netherlands, or I think this year. So I think a lot of people are looking into that. So hopefully there would be new progress on reprocessing and reuse of these single-use consumables. Yeah, but thank you.
Marta joining us from Mikkel's. Yeah, go ahead.
Can you listen to me? Thank
we
you.
can hear you now.
I'm with Mikkel here with our research that some of you now think. So congratulations, Jan, again on your presentation. And we were wondering about the logistics of who is emptying this cartridge, reusable cartridge, who is emptying them, who is disinfecting them, and who is filling them again, because I don't know if it will be the nurses. And what about the space where you will have to storage them and disinfect them in a dialysis center? That sometimes you know that the space is quite valuable, and the time of the nurses, in case they will be the ones doing it. I don't know if it will be the nurses or the manufacturers, but I'm quite interested in the logistics.
Yeah, I think that was the first main point we were discussing a lot while designing the system. And the answer to that is probably also depends on the context of different hospitals. For example, in UMC Utrecht, we have a very big sterilization unit center that can sterilize a lot of stuff, and the capacity right now is actually bigger than what we need. So it's quite new. So they also so that it can be enough for the demand for the next coming decade. So for the sterilization, we can do it in our sterilization facility. It's a central facility. And we also, in Utrecht, we also have compounding pharmacy, which have the clean room and the staff to also fill the bicarbonate in that clean room. But because of the volume and scalability, we also understand that not all hospitals are able to do this. So in this system, in the design of the system, we actually picked a third. So probably a facility that does reprocessing, so they can clean the cartridge and fill it along the way. So yeah, I think for the system and scalability, we think that's the best option, because then the clinics around the area, hospitals can send all their cartridges, used cartridges, and send it to a single facility. Yeah, but I think I think when the nurses receive the cartridge, it should be already filled by the facility. So there would be no extra burden, but then there would be that extra facility that needs to join the logistics, and that would be I think the problem. Yeah.
What about the private dialysis centers who don't have those facilities? Have you thought about that?
So we found a third party that's interested to do it. So it can be outsourced. To a third party who can clean and refill them. So that may solve the problem. So the idea is that we can probably do the pilot in our own hospital, and then we found a third party that may be interested to do it for other parties.
Yeah. So for example, the dialysis clinic in Utrecht, they don't have a sterilization facility, the normal clinics, so they can't do it like what we have in UMC Utrecht. So I think we found a third party, so another company that does sterilization of instruments and things, and they can also fill the powder and then pack it and then send it to hospitals and clinics. Yeah. Okay.
Thumbs up for Marta. Great. Unless anybody has a very final comment or question, Gareth, go ahead. Final word for Gareth. No.
A thing I always say, and I sent the data to FORAT recently, is listen, I'm not against saving water. I think we should save water, but I like to put this in perspective. I don't know what the situation is in Europe, but in the UK, our water companies lose 3 billion litres a day in leaks. That's over 1 trillion litres a year. So we had a new RO, we saved 1 million litres a year. It's not even a drop in the ocean. So I'd just like to put that in perspective. I'm not saying don't save water, but if we look at, that much water being lost before it ever reaches the hospitals or your homes or whatever, then yeah. Anyway, on that slightly depressing note.
But I think another perspective to that is not to save water, but actually it improves. It also means that if we use much less water, the dialysis ward is more resilient to supply or water. So I think that's also a nice argument to save water, not because we want to save the environment, but we also want the dialysis ward to be free of all these needs for large amounts of water and also large amounts of energy. So I think for example, the energy oil crisis happening now also could probably also justify what we're doing right now a bit. So yeah, but I think thank you for the comment. Yeah,
Gareth, Gareth, I found myself digging up that slide, so you are having an effect on me. Hoos, go ahead.
Yeah, I think to add to this discussion about savings, to be able to use RO water for dialysis, we need to heat it up from, say, 10 degrees underground temperature to, say, 36 degrees Celsius. So this is an enormous gain in electricity use when we reduce the water consumption. So it's not just about water. It's for all resources, it's a good effect.
Actually, at our unit, 60%, even more, the energy being consumed is consumed by the RO system.
Okay, I think it's clear that this discussion can continue, but unfortunately we are over time in terms of what we have scheduled, and that is testament to the wonderful presentation by Jan. So thank you again for your presentations, I should say, and for the fantastic discussion, and everybody who facilitated and who has joined.